So today we are going to see this new problem, which we call scheduling problem, and we are going to solve this scheduling problem using greedy technique. But first, let me tell you what this problem is. Okay. So schedule means like I'll be having some jobs, and I have to schedule those jobs in some certain order. Right? That's the scheduling problem. And I'll precisely tell you what are the criterias for scheduling these jobs. Right? What is the thing that I want to optimize? Those things I'll tell you. Right? So, what is the input to this problem? The input will be a set of n jobs, and along with these jobs, I'll be giving their lengths and also some weights to these jobs. Right? Uh, with positive lengths L1, L2, Ln, and positive weights W1, W2, Wn. Right? Uh, so you can think about these lengths of a job is somewhat representing the time taken to complete the job, let's say. And what does these weights represent? These weights you can think of these weights as the priority or importance of these jobs. Right? The higher the weight, the most important those jobs are. Okay, you can think you can interpret these weights and length in that sense. Okay. So when given n jobs along with their lengths and weights, so what is the thing that I need to out? So I'm going to output a job sequence. Job sequence means I have to order these jobs in such a way that minimizes a certain quantity. It minimizes the sum of weighted completion time. Now, I'm going to define what do I mean by the sum of weighted completion time in a moment. But this is the thing, I have to arrange those jobs. I have to give some permutation of these jobs in such a way that this quantity, the sum of weighted completion time, this quantity gets minimized. Okay. Now, okay. So now I'll define what is this optimization function is. Right? So weighted completion time. Okay. Uh, First thing, let's understand what's the completion time of a job. So suppose let this sigma is let this be a like it's basically the ordering of the jobs. Let's say this J J1, J2, Jn. The, this is the ordering that of these jobs. Right? So I'll say that The completion time, I'm defining the completion time of a job. The completion time of a job, let's say J, in a schedule, in a schedule. So this completion time, we're going to denote it by this. This is the notation that I'm going to use. What is this? Completion time of this job J in a schedule signal. I'm given a schedule. Right? In that schedule, what is the completion time of a job? Right? So what is this? This is completion time of a job J in a schedule delta is the sum of the lengths of the jobs uh, so voice is not okay, or just wait a second. Is it better now? Okay. Uh, the context for studying this. Yeah, we'll come to it, right? So first, you understand the problem, then I'll say what we're going to do, right? Okay. So I was defining this completion time of this job J. It's a sum of the lengths of the jobs, all the jobs that are preceding preceding J in that schedule, right? Plus the length of J itself. Okay. So what's the completion time? So if I have a job J, if I have a schedule, then the completion time of a job J will be, let's say I have, so what's the completion time of this job? To get the completion time of this job, I have to add the completion, so length of this, everything before that, including this one itself, right? So the completion time of this job J in this particular schedule will be L1 plus L2 plus L3 up to Lj. Okay. And then what would be the, this is the completion time. This is the completion time. Now, what would be the weighted or sum of the weighted completion time? That's the quantity that I'm going to optimize. The sum of weighted completion time. Right. What is this? This is of schedule. What is this? So completion time, I know. This is the completion time of the job J. Right? Weighted completion time means I have to multiply this completion time of the job with the weight of that job, and then sum of the weighted completion time. This will be like j runs from 1 to n. Okay. See, this quantity does not depend on any particular job itself. Like, so for every job, I get the completion time of the job, right? And weight of that job, I multiply them, right? And then add this quantity for all the jobs, right? So that is the quantity that I want to optimize. Right? Now, if you think about this completion time of a job, that is dependent on the schedule itself. Right? If I take a different schedule, each job will be having different completion time. Right? Now, the sum of the weighted completion time is dependent on the schedule itself. I have to if I take a different schedule, then this sum of the weighted completion time will be different. Right? So our goal is to minimize this this quantity. Right? Minimize over what? Over all possible schedule. Okay. Can you tell me how many possible schedules are there? So I have n jobs with me. How many different schedule can we form? No, not n plus 1. Anyone else? So, okay, let me give you an example. So let's say I have three jobs with me, right? And I give their lengths and I give their weights also, right? So, and these are 3 to 1. Yes, so it's a factorial n. I can have uh, mm, schedule of this job is basically a permutation of these jobs, right? So there are n jobs, so there's n factorial many permutations available. Okay, those many schedules possible. Okay, suppose I consider let's say this schedule, let's say uh, J2, J3, and J1. Right? Now, what would be the weighted completion time of these jobs? Right? Okay. So for that, what do I have to do? I have to take care of the weight of this first J2 is what is the weight of this J2? 2. Right? Now, what is the completion time of this job J2? It's just this 2. Right? Okay. What is the weight of this job J3? Its weight is 1. Okay. And what's the completion time of this job J3? Completion time of this job J3 in the schedule delta. What is it? What is the completion time of this one? It's 3. Why? Why do you think it's 3? It's this one? No, this is not 3. So what? Let me go back to the definition of completion time. Completion time of a job in a schedule this. What is this? So what did I just say? Like completion time of this particular job will be length of this job plus length of this job plus all the way up to length of this job. This is the completion time of the job J in the schedule sigma. Understand? So what is the completion time of this job 3 in the schedule delta? Yes, it's 5. So length of this, what is the length of this job? This is 2. Length of the job 3 is 3. Length of job 1 is 1. Right? These are the lengths. What is the completion time of this job? It's 2. Completion time of this job is 2 plus 3, 5. Now, what's the completion time of this job J1? 2 plus 3 plus 1. Right? Now, I think you have understood this. So, completion time of this job J3 is 5. Right? And what's the weight of this job J1? It's 3. And what is the completion time of this job J1? Completion time of this job J1 is 2 plus 3 plus 1. It's 6. Right? Yes, completion times are cumulative. Whatever, so you can think in this way that uh, what is the time that particular job has to wait to get it done? It has to wait for all the jobs, previous jobs to be completed, and then it will take its own time. Right? That's why its completion time is uh, sum of all the lengths of the previous jobs, including itself. Okay, so what is this quantity turning out to be? 22 and 5, 27, right? You get it? Now, can I arrange these jobs in some other way so that this sum of the weighted completion time becomes even less than this? Okay, let's take some other schedule. Let's say, uh, let's say sigma 1, if I take, let's say J3, J2, and J1. Okay, fine. So what would be, can you tell me what would be the sum of the weighted completion time of this? What is the weight of the job J3? It's 1, right? And what is the completion time of this job? So let me write the lengths on top of it, right? So weight of this job J3 is 1. Completion time of this job J3 in this schedule delta 1 is 3. Right? Weight of this job J2 is 2. And what's the completion time of this job J2? It's still 5. Right? 3 plus 2. What is the weight of this job J1? It's 3. What's the completion time of this one? 6. Right? What is this? even more than this schedule uh, delta. Can you think of any other schedule for which this sum of the weighted completion time gets even less? Let's say I take another, let's say delta 2. Maybe I can take J1, J2, J3. Can you tell me uh, what is the sum of the weighted completion time for this job, for this schedule? I think if you can answer this, I would understand that you have understood the problem well. Yes, it's 3 times 1, right? Plus 2 times 3 plus 3 times is it 3 times 6 or not? One time. It's like 1 times 6. Is this okay? So it's turning out to be 15, right? Okay, okay, fine. So I think everyone have understood this problem statement, right? Any question regarding this problem statement? Yes, yes. So input, again, input is some jobs are given to you, right? First page, this is the first page. So some problem statements are, sorry, like some jobs are given along with their lengths and weights, right? You have to minimize the sum of the weighted completion time. You have to schedule the jobs in such a way that it minimizes the sum of the weighted completion time. Right? Now, can you think of any process of doing this? Completion time, it's not clear. So if I give you completion time uh, is not for the whole schedule, completion time of one particular job in one schedule. It will be some of the lengths of the jobs that are visiting it and including itself. Right? You have to add the lengths. If you want to find the completion time of this job, let's think of okay. So yes, so you asked for some applications of this. These are quite useful. Like suppose you have few jobs to complete and these jobs can be completed, let's say in some one single machine. And you have only one machine and in that machine you have to perform all these jobs, right? So if you so you have to give like and your machine is such that it cannot process these jobs parallelly, like you have to give them one by one, right? So basically now you have to arrange those jobs in such a way that each of these jobs gets completed. And what is the thing that you want actually, the important jobs, right? So okay, so the completion time, so the time taken to complete all those jobs, that should be minimum, right? That is the interpretation of this sum of the weighted completion time. Okay, so can you think of a process of coming up uh with the solution? Like how can I uh So in this example, I can see that delta 2 is giving me something less, right? If we arrange in more with order, like third case. Yeah, so uh, you want to put the highest weight job first, right? So okay, yes. So that is one option, but it's not always the case. This is one special case where you have uh, ascending order of the length. Uh, yes, that's also like both of you are correct, right? Descending. So first one is basically the descending order of the weights, and the second one is you're saying ascending of order of the lengths. Both of these are correct, but in some special cases. Right? Let's understand those cases for the. I'll discuss these cases. In which case these things, these ideas will work. But before that, let's think of a naive process. Let's say I consider, uh, let's say, let's in the first step, let's say, consider all possible schedule, find the the sum of the weighted completion time for all the schedule, right? And then take the minimum one, find the minimum. So is it a correct process? So for each of these schedule, I'll calculate the. So here I have considered three schedules, right? So how many schedules are left in this case? How many schedules are left? Right. So like basically there are factorial three many scheduling possible. So I can take those things. I can take all the schedules and find their completion time. And if you do that, you'll realize that this is the minimum that you can do. Right? And I have just written that simple knife process. Right? Is it a correct algorithm? Why not? It's in fact this is correct algorithm, but not. It's not efficient because the computational cost will be very high. Right? What's the running time of this? Running time of this O of n. Why is O of n? How many schedules are there? as you told that there are factorial n many schedules possible, right? And once you have this schedule, so you have to run a for loop for these many times, factorial n many times. And once you fix the schedule, then how much time would you take to how much time would you take to find the sum of the completion time of that particular schedule? That will take it's O of n time, right? And finding minimum out of those n quantities again n O of n. Right? Now, which one would take n log n? Finding minimum, I'm not sorting them. Sorting takes me n log n time, but I'm just finding the minimum, right? So minimum I can do in O of n time. Right? So overall running time will be factorial n. Right? It's even more than exponential, exponential running time. Okay. Okay, fine. So this is correct algorithm, but not an efficient. Okay. So now let's understand the two cases where your ideas will work. So one idea was arrange the job according to the decreasing order of their weights. Right. Uh, let's see. Uh, mm, Case one. Let's consider that all the jobs as equal length, right? Okay. So equal length, let's say one. All the jobs are having length one, right? Now, can you tell me what would be, so if you consider any schedule I consider, mm, so there are n jobs, right? What is the completion time of the first job? This, this is any schedule. What is the completion time of the first job? Each job lengths are one. Okay. Yes. Anyone? First job, completion time of the first job is one. What's the completion time of the second job? Right. Completion time of the second job is two. Then the third job is three. The last job is n. Right. So it's for any schedule, the completion time of these jobs will be one, two, three, four up to n. And that is fixed since the length of every job is one. Right. So now think about the quantity that so uh, for some schedule, I'm what do I want to compute? So weight. So here I'll have some weight, and then I'll have the completion time of the first job. Then I'll have the weight of that particular job and the completion time of the second job. Right. Then I'll have this completion time of the third job, like this. Right. And I'll do it for everything. And the last job, completion time of the last job will be this. Okay. So which weight do you want to put here so that overall this quantity gets minimized? You understand the question? So whatever 1, 2, 3, 4, these are the things that I have written here. These are the completion time of the job. Okay. Now, if you want to minimize this function, if you want to minimize this whole function, what is the thing that you want to put here? Which weight should I put here? No. So if I put the minimum weight, let's say weights are, let's say again 1, 2, 3, 4, 5, right? So if I put the minimum weight 1 here, 2 here, and then n here, then this will be a maximum. This thing will be maximum, right? So it turns out like one, it's like one square, two square, three square, up to n squared, right? Sum of all of this, right? It's like n cube, order of n cube. Rather than that, if I put the maximum weight here and then the second maximum here, like this, right? And then I can see that this is going to be something in square, even less than that. So here I should be putting the maximum weight here. Right? Then I'll put the next maximum weight. And at last I'll put the minimum weight here. Right? So when, in this case, when all the jobs are having equal length, then what is the schedule that we want to do? Optimal schedule that should be what? Uh, Jobs arranged in decreasing order of their weights. Is this clear? Okay. So this is one case where one of the idea is working. So as I said, like you can schedule the job like maximum weight job first, then the next maximum weight job in this way. But that will work when it has all the jobs have equal length, right? But one thing you must understand that uh, in this situation, you cannot decide you cannot decide in terms of lens. The other idea that someone else had said, what was the other idea? By increasing order of their lens, that will not work because everything has equal length. Which one would you put first? Like that idea will not work, right? So let's consider the other case. I think you can guess what is the other case. All job weights are identical. Job weights are same. Let's say, right. Then what would be the, let's say, first completion time of this one is suppose L1. This is the completion time. And then I have to multiply with the weight. And the second one will be having completion time L1 plus L2. Right. The next one will have completion time L1 plus L2 plus L3. Right. So what is L1? So like let's say I have scheduled the jobs in this order. This is L1 is this one, L2 is this one, L3 is this one. Right. So what is the time for completion time of the last job? L1 plus L2 plus all the way up to Ln. Right. This is the quantity. I want to minimize this quantity. Right. And see, everything, every weights are the same. So what's the actual meaning of length? Meaning of length of one job. You can think that length of one particular job is the time taken to complete that job only. Okay. So if length is 5, then I can say it takes 5 minutes to complete. Okay. Since I have taken, so I want to minimize this quantity, and W is fixed for weight of every job is fixed. That's W. Right? Now, which job should I put first so that this whole thing is minimum? See, in this summation, so I can take no, it's not any job. It will not be any job. What is the sum here? If I add this thing, so this will be so this quantity will turn out to be this. How many times this L1 is added in this one? So I can take this W out, right? Mm. Just a second. Okay. Yes. So you so L1 is added n times. So it will be n times L1. Right. So then n minus 1 times L2. Second job that I have put, the length of that job will be added n minus 1 times. And this one is. And how many times the last job ln is added? It's only once. So now you can think which job you want to put first so that it total contribution will be less. Like I want to minimize this quantity, right? Which L1 should you put first? Maximum, if you put L1, if the maximum length, that job you want to put first, then that will be multiplied by n, a big number, right? And the second max is multiplied by n minus 1. You should actually do the exactly the opposite of this. Minimum length job you should put first. The second, then the second minimum. right? So in this case, the optimal schedule as that would be like shorter length job should come first. Okay. Yes. Any question regarding this? So these are the two extreme cases when in one case you have all the jobs are having equal length, and there we have just observed that I have to arrange the jobs maximum weight job first. And when the job weights are identical, then I have to arrange the minimum length job first, right? Like this. Okay. But these are the two extreme cases. But in practice, we get a mix. We don't always end up with these special cases. So what we do here is uh, okay. So our strategy is that we are going to assign some score to each of these jobs, right? And schedule the jobs based on the decreasing order of the scores, right? I want to settle the score in such a way that it takes care of these two special cases. Okay, so let me write my strategy. Right? So for the general case, we assign a score to each job so that scheduling jobs from highest to lowest is guaranteed to minimize the sum of the weighted completion time. Also, the scores must, not should, must uh, satisfy the two special cases. Right? Is this a strategy okay? So I want to, for each of these jobs, I want to assign some score to it. And then I'm going to arrange these jobs in uh, in in the decreasing order of these scores. Right? So I have seen two cases. One, what are the two cases? In one case, I have to arrange the jobs in a decreasing order of their weights. And in other case, I have to arrange them in the increasing order of their lengths, right? These are the two cases. Keeping these two cases in mind, can you assign some score to these jobs so that I can arrange the job in and according to decreasing order of their scores, right? And still these two cases will be satisfied. What type of score I want to put it? Some score means some value I want to put it based on the like depending on the weights and lengths of these jobs. Okay. For example, let's say I want to put the scores to be, let's say, Wj minus Lj. This is one option, right? So for each of these job, I compute this W1 minus L1, W2 minus L2, Wn minus Ln, right? All these things I calculate and I arrange these jobs based on the values, decreasing order of the values of Wj minus Lj, right? That will take care of the two extreme cases. Right? Think what is happening in here. If I arrange these jobs in this order, right? If length of all the jobs are same, right? Then decreasing order of these scores is will actually mean the decreasing order of the weights, right? So when lengths are same, then we are actually taking the jobs in the decreasing order of their weights, right? Now think of the other case. When the weights are all same, right? Then the decreasing order of the score will actually mean the increasing order of the lengths, right? Because it's minus L1, minus L2. Decreasing order, increasing order of minus L1, minus L2, minus Ln, that will actually mean the increasing order of the lengths, which will actually satisfy the second case as well, right? So this is a valid score I can take. This is not the only score I can assign to it. I can assign many other scores. For example, I can also think of the ratio of these two. Wj minus Wj by Lj. Yeah. So by this I mean like I'll calculate these quantities and arrange the jobs in this one. Okay. Now it turns out that this like I'll put this name greedy difference. Right? So when I'm putting the scores as Wj minus Lj, I'm calling the score as greedy difference, and here I'll call them as greedy ratio, like this. So let's understand this by an example. I take even simpler example. Right? So lengths I take as 5 and 2, and weights I take as 3 and 1. Right? Uh, so Greedy difference means Wj minus Lj. So what is this? Wj minus Lj is minus 2. This is minus 1. Right? And ratio is Wj minus Lj. It's 3 by 5 and 1 by 2. Okay. What is the, so let's say, what would be the schedule if I arrange the jobs based on the decreasing order of the difference? This is the difference, and this is the ratio. Can you tell me what would be the, which job should come first? If I arrange the job in the decreasing order of the difference, which job should I do first? What are the difference values? Minus 2 and minus 1. I have to arrange the jobs in the decreasing order of this difference. What would be the order? Yes, J2. J2 should come first and then J1. Right? And in terms of ratio, what would be the ordering? So J1 should come first, then J2 in terms of ratio. Okay. See, both the cases are satisfying the two special cases. Both the scores satisfies the two special cases. Right. Now let's see which one gives us the minimum. So these are the only two options possible. Either J1, J2 or J2, J1. Right. Which one would you give the optimal? Can you tell me what's the sum of the weighted completion time for sigma difference? Yes, what would be the C of delta difference? What is the weight of the job J2? It's 1 times. What is the completion time of this job J2? 2, right? And why it's 13? Yes, 1. Oh, okay. I suppose it's 1 and 3. So what's the completion time of the job J1? Yeah, so weight of the job J1 is 3 and completion time of the job is 7, right? So it turns out to be 23. And what about the ratio? The weight of the first job, first job is 3, right? The completion time of the first job is 5, right? And the weight of the second job is 1 and the completion time is 7, 22, right? Okay, so clearly this one gives you the optimal schedule. Okay, ratio will be the optimal solution. Correct. So how can you say that this is the optimal one? This is okay. In this example, it's the optimal. Right. I think that to find both and compare the solution. No, no. For this particular example, I'm saying that we have only two options. Since we have just two options, then it's easy to find that this is giving you the optimal solution. Right? Think about the situation when you have 10 jobs, let's say, right? And you arrange them in these two, right? They are maybe greedy difference and greedy ratio. And you see that greedy you greedy ratio is giving you better result, right? But what is the guarantee that there does not exist any other way of setting up this course so that I can get even better optimal value? What is the guarantee for that, right? That is the thing that I'd like to convince you now that it's true that when you arrange the jobs according to decreasing order of their score, right, and decreasing order of their greedy ratio score, then you are always going to get the optimal solution, right? So let me just now uh, state this one. Let put jobs arranged in decreasing order of, say, ratio gives the optimal solution or optimal schedule. Okay. So this is the point that I want to clarify. Any question till this point? Yes. Okay. Fine. So let us. So what we are doing here, I'm arranging the jobs in. Let's say our algorithm, greedy ratio algorithm, gives me this schedule, like J1, J2, Jn, right? And what does that mean? This means that these ratio that you have calculated, right? So suppose this is the output of this one, greedy ratio. Right. what can you say about these values? Wi by L. These are the ordering because in this process we are putting which job I should put first. J1 I'm putting first. That means this J1 must be having the maximum ratio, right? Okay. Now see that consider any other schedule. Let's say delta cat. Right? So in that schedule, oh, okay. So which one would you like me to repeat? Uh, so is this clear? What do I mean by greedy ratio output? Oh, okay. So this whole page. Okay. So what we with this example, what we have observed that greedy ratio gives you the optimal schedule, right? But what have we done in here? There are two possible scheduling. I have checked their values for both of them. That's all. Since I know there's no other schedule, I can say that this greedy ratio gives me the optimal. But when I have more than two jobs, like let's say 100 jobs, right? There will be factorial 100 many uh, permutations or schedule possible. I'm not going to compute all of their some of the completion times, right? Weighted completion time. So I have to now justify that why I am saying that if you arrange the jobs in the decreasing order of their ratios, then that will give you always the optimal schedule. That is the point I want to make clear. So the job arranged in the decreasing order of their ratio gives the optimal schedule. Understand this? That is the thing that I want to convey. Hope it's clear now. Basically, I'm looking for the proof of correctness of this algorithm. Okay. So in this one, what's my assumption? I'm assuming that my algorithm gives outputs this schedule, right? J1 job first, then J2, then Jn, right? That means what? These jobs are arranged in decreasing order of their ratio. So that means W1 by L1 is the maximum, then W2 by L2, then Wn by L, like this. Right? If I consider any other schedule and compare with the schedule that I'm getting out of this algorithm, right? Let's compare these two. Then what would happen in this case? What would happen? Okay. So this contains pair of jobs. A pair contains a pair, let's say I comma j, pair of ij, such that I is more than j and I, the job I is processed just before the job J. Okay. So, for example, let's say consider five jobs. Let's say this is one, two, three, four, five. This is the output, the job output. We won't use difference. No, difference will not give you the, I'm not using this difference because I can see clearly that difference will not give me the optimal, right? I'm getting the ratio is giving. Okay. So I have two options, difference and ratio. I can see that ratio is giving better result than difference. Okay. But what is the guarantee that this ratio gives me the best possible output? Only this working out with an example is not sufficient. I have to prove mathematically that this will give you the optimal solution. Although I'm not going into the details of the whole proof, but I'm trying to give you an overview of this. So here this is the output. Suppose five jobs I have, and this is the output that I'm getting. Can you think of any other schedule other than this? In that schedule, you must be having two consecutive jobs where I is more than j. And think about any, let's say 2, 5, 3, 1, 4. So I'll have, can you find a pair ij in this thing where I is just before j and I is more than j? Can you tell me? Suppose this is my I, this is my j. I is more than j and I is just before j. The job 5 is coming just before job 3. Okay, right? So what I do, so I'm going to alter these things. Suppose that if we want to, we want to show that this is optimal. So what we do, our strategy will be like if if this is not optimal, then suppose this is the optimal, this is the delta star is the optimal. There must be some other schedule which is different from this delta, right? And in in delta, just what we have just argued is that in this delta, we must have a pair ij such that I is greater than j and and the job I is processed just before before j, right? Uh, this is a process just before j. Okay. Now, what we do, we interchange I and j. So what would happen in sigma star? What we had? I have somewhere I had this job I and followed by job j, right? So I after I interchange this, I'll get some other schedule where everything remains the same, and then j comes first and I comes after it. Okay, I interchange those two jobs. Everything else here and here, these are the same. This is the same. These jobs are the same as this one. Only difference between this delta star and delta dash is I and j. Now we can show that we can show that some of the completion time of this is less than some of the completion time of this delta star, right? That will come from the fact that uh, I is more than j, right? So that means what? Wi Li, right? So Wi Li will be less than Wj Lj. You just check the completion time and you can show that it will happen that you can get another schedule whose completion time is even smaller than the optimal one, some of the weighted completion time. Okay. That is not possible. So since we have assumed that this is the optimal one, so we arrive at a contradiction. What is the contradiction? That this delta star is not the optimal one. So if this is the optimal one, I cannot be having something better than the optimal one, right? That's a contradiction. Okay, so okay, this is a rough idea of how to go about the proof of correctness. Although I have not gone uh, in the details of how to show this one, right? Uh, if you are interested, you can check this proof, but it's not. It's useful, or it's useful. Uh, Running time. Uh, okay, so you must be. You should check the proof there, right? Although I've not gone through the details of the proof, but I've just told you the idea of what. Right? So what we have assumed that this is important. This fact is important. So if you consider any schedule other than the output, then you must be having some pair I and j, where I is more than j and I is processed just before j. right? And once you have such a case, you interchange these two jobs. And by interchanging these two jobs, you can get another schedule which whose some of the weighted completion time even smaller than the optimal one. And that's the contradiction. Okay. Yes, this is the running time page. Which one is this the one that you want? Question? Okay, fine. So then we can stop now. You so out of this class, you must understand what is the process of finding the proper schedule. Right. So it's the algorithm is just when you have all these jobs along with their weights and lengths, you just find the ratio Wj by Lj and arrange the jobs according to decreasing order of this ratio. And that's it. That's the algorithm. And we also have just tried to explain why this should give you an optimal solution. Okay, okay, fine. So if there's no other question, then I can I should close this meeting now. Uh, okay, so I cannot answer this. What to do in that situation? You must talk to the admin.